Our chapter 10 was all about areas, finding areas of different shapes. Okay, and along with that came a whole bunch of formulas. Okay, so these are the ones that are going to show up for us final time. Now, a lot here, don't panic, you probably have a lot of these memorized already. Okay, a few new ones this year, such as trapezoid and regular polygon. And then a few of these will show up actually on your formula sheet, such as the area and circumference of the circle. But do take a second, copy these down. Okay, make sure you have a spot to study these. And then in a minute here, we'll show you how to use them in our different problems. Okay, first problem is going to use some of our basic area formulas, but to find the area of a composite figure. Okay, a couple figures combined into one. Problem 1 just says find the area of the figure, round to the nearest tenth. Okay, and it looks like what I'm looking at is made up of a rectangle and a half circle. Okay, so we'll use those two formulas separately here. Kind of the idea with a composite shape is to find the areas separately and then add them together or subtract them or divide based on whatever that shape looks like. Here we'll just add the two parts together. Okay, so we have the rectangle. We said area was just equal to base times height. Okay, and for base and height, it doesn't matter which side we use as the base, which side we use as the height. We just need to multiply the two dimensions together. Now the issue with this problem is that I know one of those dimensions, we'll call it the height 7. Okay, I actually don't know the length of my corresponding base then, because this 19 takes up the entire figure. It's not just this length here. Okay, so a little problem solving we have to do. To do that, this 7 on the left side, since we're assuming this is a rectangle, I can drag it over to the right side and say that's the diameter of my circle. Okay, which means for this half circle here, if the diameter is 7, the radius is going to be half of that, 3.5. Okay, so my base then will be the 19 minus 3.5, which will be 15.5. Okay, so like we said, little problem solving, our area is going to be equal to the 15.5 times the 7. And I'm ending up with 108.5 inches for the area of the rectangle. Inches squared, I suppose we should say. Okay, so we're halfway done. We've got one of the shapes taken care of. The next thing we're going to look at is the circle. Okay, area of a circle is going to be equal to pi times the radius squared. Notice I'm leaving some space here for a reason. Okay, we found the radius already, so we're good there. Now the issue we have here is that we're only going to look at finding the area of this half circle. The other half we already calculated as part of the area of the rectangle. So we want to know the area of the half circle, which means we'll just take the area formula times a half. So in this case, just half times pi times radius squared. I suppose technically we're calculating the area of a sector of a circle. Okay, half of the circle. Okay, so to do that, we'll go half times pi times 3.5 squared. And when I do that, I end up with 19.2 inches squared. Okay, we could leave things in terms of pi, but since our first answer doesn't have pi involved, it wouldn't make sense to really do that. So final answer then, our composite area will just be equal to the 108.5 plus the 19.2. When I do that, I end up with 127.7 inches squared. Okay, that's actually not up here for one of your choices. I've got to fix that. Test time, things will work out nice. Okay, but 127.7 inches squared for a total area. Okay, problem 2, we're dealing with trapezoids. It says, what's the area of the trapezoid? Round to the nearest tenth. Okay, so we could think of this as a trapezoid, or I suppose a composite figure where we have a rectangle and triangle combined. Either way, we're going to have to use some problem solving. Okay, formula for area of a trapezoid was area is equal to 1/2 times the height of the trapezoid times base 1 plus base 2. Okay, when we're talking about the bases, we're talking about the two parallel sides of the trapezoid. Okay, for our formulas, we want to fill in what we know. We know the half. I actually don't know the height of this trapezoid right off the bat. We'll have to solve for that. But I can figure out my two bases right away. One of them is just 7. Then we can say plus, the other base will be 4 plus 7. Okay, so 11. Okay, so I have to solve for the height then. And trick in solving for the height, I can break things down into triangles. And once I've done that, we can use our special right triangles, trigonometry, or in this case, Pythagorean theorem. We have a right triangle where we know 2 of the sides. We can solve for the third side, we'll call that h. So I can set up that h squared plus 4 squared is equal to the hypotenuse 8 squared. So solving for h, we can subtract 4 squared from 8 squared. That'll give us h squared is equal to 48. Take a square root of both sides of the equation, we end up with h is equal to 6.9, we could say. Okay, so we have that height then, 6.9. Now we can actually figure out the area by multiplying things through. And when I multiply in what we have, I end up with 62.1. Okay, closest real answer is 62.5. Now the reason I'm off by 0.4 is instead of 6.9, we could have called this 6.9282. And it's that extra 282 that kind of makes us miss this 0.4 here. Okay, so multiple choice times. A lot of times you need to ask yourself, is my answer close enough? Okay, can I circle one of those? In this case, I'd say for sure we can. All right, problem 3. This is one of our trickier ones from chapter 10, finding the area of regular polygons. 3 just says, find the area of the regular hexagon, round to the nearest tenth. Okay, formula for regular polygons was area is equal to 1/2 times A for the apothem times P for the perimeter of the polygon. Okay, we can find the perimeter by just taking the side length and multiplying it by the number of sides we have. Okay, the trick for this problem is we don't know what the apothem is. We define the apothem as the segment going from the center of the polygon to a side at a right angle. We'll call that A. So the whole trick for this problem is going to be solving for that apothem. Okay, the way we did that is we broke our shape down into right triangles. Now, since the side length is 6, half of that side length for solving for my apothem is just going to be 3. Okay, the other thing I need here then is an angle. To do that, what I'm going to do is I'm going to start off with a separate triangle. Since it looks like I could break my shape down into 1, 2, 3, 4, 5, 6 different triangles, we can take 360 divided by 6. Okay, because we're talking 360 degrees in an entire rotation around here. Divide that by 6, that's going to give me 60-degree angle. Okay, now if I take that angle and divide it in half for this half-size triangle, we end up with a 30. Okay, so now I can look to solve for that A using the right triangle and the angle and the side length. Okay, we could use our 30, 60, 90 right triangle, those properties. Okay, but I'm thinking most students are going to do this through trigonometry. We know an angle 30. We know the opposite side. We have to solve for the adjacent side. That's our tangent ratio. So I can set up that the tangent of 30 is equal to opposite 3 over adjacent A. Okay, solving that for the A, we'll multiply both sides by A to get rid of the fraction. Cancels the A on the right. So we have A tan 30 is equal to 3. Okay, finish off by dividing both sides by tan 30. Okay, tan 30's cancel, and we end up with A is equal to 3 divided by the tangent of 30. Okay, plug that in. I end up with 5.2, rounding to a tenth. Okay, so finally we have the apothem. Now we can solve for the area. We can say that area is equal to a half, okay, times that 5.2 we found, okay, times the perimeter of our regular polygon. Side lengths are 6, and there's 6 of those sides, so we can multiply the two of those together. Okay, plugging that in, I end up with the area is equal to 93.6 meters squared. Okay, so it looks like option A here for us. Okay, basically final time, probably be the same idea. We have the formula for the area of a regular polygon, but you're probably going to need to solve for something, okay, using trigonometry, using Pythagorean theorem, special right triangles, to get that piece you're missing. Okay, our next problem, problem 4, deals with area of similar figures. It says it costs a family $100 to carpet an 8-foot by 12-foot bedroom. If they use the same carpeting in the living room with dimensions twice as long and twice as wide, okay, how much can the family expect to pay? Okay, so we have two rectangles. They're similar. One's just twice the size of the other one. Now it would be tempting here to just take $100, multiply that by 2, end up with $200. Okay, circle that for a solution. Okay, things don't quite work that way when we're talking about similar figures in area. Okay, what we gave you is we said if we have a scale factor between two similar figures of A over B, we said that the area scale factor is going to be equal to A squared over B squared. Okay, so for this problem, no proportion that we need to set up. I suppose we can take the 8, double it, set up a proportion. But all I need to do is multiply by that scale factor. Okay, so we'll take the 100, and I'm going to multiply that by 2 squared. Okay, so in other words, 100 times 4, which will give us $400. Okay, so pay attention. One of the tricks with this test is there's going to be proportions. Proportions, you need to do some squaring and also cubing when we get to the volume section. Okay, so be careful. Don't just circle the kind of closest nice answer. Make sure you take care of your scale factor properly and make sure you're dealing with either a side length, an area, or a volume. Okay, make sure you adjust it for that. Okay, our last problem deals with parts of a circle. It says 5 streets come together at a traffic circle. The diameter of the circle traveled by the cars is 200 feet. If traffic travels counterclockwise, what's the approximate distance from East Street to Composite Street, we'll say? Okay, so what's that distance? Okay, so what this is asking here is we have East Street. We have a car that's going to enter here, and it's going to travel counterclockwise until we get to Composite Street, like this. And we want to figure out what distance the car is traveling here. Okay, what we're technically talking about here is the length of an arc of a circle. Okay, if we have the entire circle, we can figure out its length or its circumference. An arc length is going to be a fraction of that. Okay, the way we'll calculate that is we know how to find the entire circumference of a circle. That's just 2 times pi times the radius. With an arc length, what we added in was we looked at the measure of the arc in degrees divided by 360. That's going to give us the kind of fraction or the percentage of the circle we're dealing with of the entire circumference. Okay, so first thing we'll figure out is that for this arc length here, it looks like I'm 40 degrees short of 180. Okay, so 90 plus 40 will give me 140 degrees for an arc measure. So setting our equation up, we can say we have 140 over 360. So there's our fraction of the circle. And then we're going to multiply that by the entire circumference. Okay, we can say 2 times pi times r, or since we know the diameter is 200 feet, we can just say pi times diameter. Okay, multiply all that through, and I'm ending up with approximately 244.3 feet. Okay, so we'll circle option B, 244 feet. Okay, yep, we have a new formula to kind of memorize here, but if you remember how it works, it's really just circumference times the amount of the circle we found. Okay, same kind of thing we can do for finding areas of sectors, areas of fractions of circles.